Welcome to today's webinar. My name is Jeremy Heenek. I also have David Wiseman and Rachel Evans on the line. And today the topic of the webinar is why we're technically the best. It's quite a bold statement, but I think you'll understand it better as the webinar goes on. We've all been here for a very long time. Over the years, we've helped with evaluations of thousands of evaluations of the FaultTree analysis tool. And throughout that time, different people are looking at different things and different people have different requirements. But we learn about a lot about what's on the market, what people do, what people don't do. And so over time, is the audio working? Someone mentioned they're not getting audio. Can you hear me, Rachel? Valentina?
I can hear you.
I can hear you.
Okay. Sorry. So anyway, so over that time, we've kind of accumulated, not a list, just an idea of what we're best at. And FaultTree Plus, if you're looking at specific things that we'll go over today, that we really are a sole source type of tool. There aren't many that can handle the type of calculations we'll be talking about today. And that, not to make it sound too salesy, it's good to technically understand what those things are, and that's what David will be very good at. I know David isn't going to talk about himself much, so I'll help introduce him. He has a PhD in nuclear structure, which is, from what I understand, a very difficult degree to get. He loves Liverpool soccer, and for those of you over in Europe and even in the US, they won the Premier League this year. So David's really is living his best life right now. And David will be giving most of the presentation. I'm just introducing what's going on. Just a few housekeeping items. You'll notice, for those of you that haven't been in team meetings or that have, please, you can use both chat and Q&A. We prefer you post the questions in Q&A because it's easier for us to manage what's going on, but we'll keep an eye on both. But Rachel, who will be watching the Q&A, she'll be watching Q&A closely. Maybe I'll watch the chat. And then Rachel and I will respond to those as they come in. We'll be pausing for questions. So feel free to ask your questions. If they don't get addressed, we will address them, whether it's to you personally. We'll post this on the blog afterwards and maybe give some generic questions that were asked during the meeting. David, do you want to go to the next slide really quick? And just a recap, I know a lot of you know this, some of you may not. Isograph is part of Peak Avenue, where we're kind of merging with several other companies. We have a new member of our family, which is Osino, which I bring them up specifically because I know a lot of you do requirements management. They call it requirements engineering, but it's down those lines of requirements engineering, requirements management. And this will also become a part of our family as well. So if that's something you're interested in talking about, reach out to Rachel or I, and we can kind of continue that conversation as well. If you can think of anything else, David, let me know. Otherwise, why don't I turn this over to you and you can get started.
Yeah, thanks very much. Hi, everybody. So Jeremy gave a very nice introduction for me earlier. Anybody who follows football might debate whether I'm living my best life right now. but yeah, let's set football aside for now. And I'll talk a little bit about what we'll be looking at today. So yeah, this webinar is going to talk about what it is that sets FaultTree Plus apart from other FaultTree tools that are out there. Now, Jeremy was saying we don't want to make this too salesy, because I could sit here and point to any number of checkboxes and drop-down boxes and options. You can fill a software tool with all kinds of options and market it on that basis. Problem is, if the calculations don't work, then all the options in the world make no difference at all. And that's where FaultTree Plus excels, in the fact that it can handle large fault trees, that it can return the results in an efficient and accurate way, and it has different methods it can use to do that. Its stability and its accuracy are not really challenged by any of the other tools that are out there. The analogy that I make is to purchasing a car. When you buy a car, you could buy a car that has the best sound system in the world. It has the most expensive upholstery, has all the latest gadgets on it. But if the engine doesn't work, then basically all you have is a very expensive, very small living room. So if the engine of your car doesn't work, doesn't matter how many optional extras you have, it doesn't mean anything. And it's the same idea here. So I'm going to begin with a little bit of background for what I'm going to talk about. Now, a disclaimer, I am going to assume a degree of knowledge from the audience on fault tree analysis, because I don't think we'll have a lot of time to dig into the basics of fault tree. So I am assuming that people in the audience kind of understand about basic events and logic gates, and maybe a little about minimal cut sets too. And I'll be proceeding on that basis. After that, we'll start talking about the fundamental things that make FaultTree Plus work, and that make it work really well. These are the ideas of things like modularization, the different quantification, different calculation methods the program can use to get to the result in the quickest way and the most accurate way possible. And if there's time, I'd like to take a look at a couple of the other analysis techniques that are kind of packaged in there to help you make the most of the results that the program is giving you. At the end of all that, then we'll have our Q&A. So to begin with, a little bit of background. So like I said, I'll assume a degree of knowledge about fault trees, so I won't explain about gates and basic events, but I will say that a fault tree analysis breaks down basically into two steps or two types of analysis. The qualitative analysis, where the program works out all the different possible combinations of events that can lead to a particular hazard or top event. And second step, the quantitative analysis, where the program calculates the probability with which that event, that hazard occurs, based on the probabilistic data provided at the basic event level. So failure rates and repair rates, stuff like that. So these are the two fundamental steps that the software goes through when it analyzes a fault tree. Now that's the same for every fault tree, big or small, but of course large fault trees can be particularly challenging. There are lots of tools out there, but maybe not all of them are well suited to handling big fault trees. That maybe they kind of fall over if the fault tree is too big. Maybe they start running and there's no end in sight for when the analysis will finish. Maybe it can finish the analysis, but there are questions over the accuracy and the methods that are used. So I want to give you some insight into how FaultTree Plus overcomes some of these challenges. Now, I was trying to think of a way of doing this that's better than me kind of jumping back and forth between the software and the slides. I couldn't think of one, so unfortunately that is what I'm going to be doing. I'll try not to let it disrupt the flow of the presentation too much, but I do want to show you this stuff working to give you a little bit more insight, because there are probably people in the audience who've been using the software for years, have seen some of these options, but not really understood yet exactly what they are or what kind of impact they're having. So I want to try and give insight into that, not just for new users, but for those of you who've been using the software for a while. One really important concept that the software makes use of is modularization. Modularization is a process whereby the program will solve each gate individually, then pass the result of that analysis to the next level of the tree for further calculation. So essentially what it's doing, instead of working out all the minimal cut sets for the top gate all in one go, and then doing a huge probability calculation for that one big set of minimal cut sets, for each gate, it will work out the minimal cut sets, calculate the probability of that gate, then sort of package it up as a kind of super event before passing it to the next level. Now, the program is smart enough to automatically decide which gates it should or should not modularize, which gates can be solved on their own, packaged up, passed to the next level, and which ones should be left unmodularized with all the cut sets and so on passed to the next level. It does this based on whether or not the gate is independent of all the other gates in the tree. So if there are shared events and gates beneath that gate, if it's sharing some structure with another part of the tree, or if it has like a common cause failure going on in there, it will not be modularized. It will be left unmodularized, as we say. So the program knows the difference, and it will modularize where appropriate and will not do so if not. If it were to modularize a gate that had those dependencies would be broken, and it would result in an inaccurate calculation, potentially one that's overly optimistic. So the program knows not to do that. So that's a kind of hand-waving explanation of what modularization is, of effectively solving individual gates on their own before passing the result up the tree to solve the next gate, taking that result, passing it to the next gate. What impact does that have on the actual analysis? For one thing, it makes the analysis faster. Instead of trying to solve the probability for 100,000 cut sets at the top gate, I can do the entire tree piecemeal, bit at a time, and have a much simpler calculation when I get to the top. So it makes the calculation faster. It can also make the calculation more accurate. That one might not be as obvious. Reducing the size of a probability calculation obviously makes the calculation faster. Why would it make it more accurate? I'll come back to that. So that's modularization. Basically, that the program is solving individual gates where possible, if they're independent from the rest of the tree, packaging it up and passing it to the next step of the tree for further calculations, reducing the overall size of the probability calculation. And it knows to do it automatically. So what about the calculation methods? So we talked about modularization and how that speeds up the probability calculation. But how is that probability calculation actually done? What methods are there? So there are 3 different methods that the program can use to calculate the overall probability of a gate in a fault tree. These are the cross product, the Esary Proschan and Rare approximations. Maybe you've seen them in the options for the program. I'll be showing you where those are shortly. And or maybe you've come across them in the help or somewhere like that. Maybe you've done a training course with us and remember these terms but can't quite remember what they mean. So we'll be looking at what they are and how they help us, in what context each of these methods might be used. It is worth noting, though, that while Esary Proschan approximation and Rare approximation can be selected manually, the cross product cannot. Instead, there is an optimum upper bound method where the program will automatically select which of these 3 methods gives the most accurate result. So again, it's the program being smart and helping to make the calculation more accurate, basically by trying different methods and see which one gives you the best result. Again, I'll talk through exactly how that works. Let's have a look first at the cross product. So we've all had the traumatic experience of learning probability while at school. You know, the teacher says, okay, I've got 3 coins and I flip 3 coins. What is the probability that I get a coin, at least one coin, landing on heads? And then, you know, we all sort of hunker down behind the desk and try and avoid eye contact so the teacher doesn't ask us what the answer is. This is the same fundamental principle upon which FaultTree calculation is based. It's hard to believe that, really, that simple idea, you know, what's the probability of one thing happening or another thing happening, is the basis for something as complex as a fault tree. But as big, as complicated as a fault tree can become, those ideas remain the same. In a fault tree, all you're asking is, what's the probability that cut set 1 happens, or cut set 2, or cut set 3, so on. And for something like that, we'd use a concept called the addition law. Now, I am oversimplifying a little for the purpose of the webinar, just because, you know, I could spend a couple of hours talking about this potentially, and no one wants that. So I'm going to keep it very simple and say, you know, let's say we've got a fault tree with 3 minimal cut sets. If I want to know the probability that at least one of those cut sets happens, I would add the probability of the 3 sets together, subtract every combination of 2 cut sets happening at the same time, then add back in the probability that all 3 cut sets happen. So we are successively adding and subtracting terms until we get to the correct answer. People often wonder, you know, why can I not just add those 3 probabilities together? Is that not how you work out an OR gate? Do I not just say, well, I'll just add the probabilities up, and that's the probability that at least one of those things happens? This Venn diagram on the right illustrates the problem with that. I've got 3 cut sets. Each circle represents the probability of that cut set happening. Where 2 or more circles overlap is the probability of 2 or more cut sets happening. So for example, this bit is the probability of cut set 1 and 2 happening together. If I were to simply add the 2 circles together, I would be double counting the area where they overlap. That's why I need to subtract it, to avoid double counting cut set 1 and 2 happening together. Of course, if I subtract every area where 2 circles overlap, I'm completely removing the bit in the middle where all 3 cut sets happen, which is why I have to add that back in. So basically, that's the addition law and how it works. Again, there's an extra layer to that with cut sets, but I don't want to dig into that for the purpose of today. Treating it very simply, that's how it works. Problem is, you're unlikely to see a serious fault tree that only has 3 minimal cut sets. So it's easy for me to use that as an example to explain how it works. But what if a more realistic scenario were to occur where I had hundreds of sets or thousands of minimal cut sets? Suddenly this Venn diagram becomes, well, unreadable. And how do I do that calculation? Well, the way that process works is basically exactly the same. It's just instead of add, subtract, and add again, you're adding all the cut sets together, subtracting every combination of 2, adding every combination of 3, and so on through, you know, combinations of 100, 1,000, 10,000 cut sets. And you can kind of imagine it graphically, where you're adding all the combinations together, subtracting every combination of 2, adding every combination of 3, and so on. So you're kind of incrementally getting closer and closer to the correct answer. Now ignore the numbers on here. I've just used this to illustrate the points. This is from a different example. But basically, you can imagine a kind of wave that's getting smaller and smaller as the answer gets closer to the correct number. So how can we speed this process up without losing accuracy, and how can we test for accuracy? Well, of course, this calculation, if you've got thousands of cut sets, could have many thousands, millions even, of terms as you add, subtract. Do you need to go through all of them? Once you're getting up to, say, combinations of 100 cut sets or something like that, the numbers you're dealing with are so small, you probably don't need to worry about them anymore. They're far below the level of precision that you're looking at. So maybe we can set a terms limit. So I'm going to stop there, jump out, go into the software. So I've got a little FaultTree here. It's not huge, but it's just good enough to illustrate some of the principles I'm talking about. So in the software, I'm going to go and have a look at the custom options. I always say to people that we kind of bury some of these options deliberately. These are the ones that can affect the result of your calculation. So we put them in a place where it's least likely that you would accidentally change something and cause a problem for the calculation. So you're really not going to change anything here unless you really mean to. So here is where I can choose between the different methods. I'm going to stick with optimum upper bound. But I want to point out here where I've got a product terms limit. So remember, I said that the program will add the probability of all the cut sets together, then subtract every combination of 2 cut sets, add back in the combinations of all 3, and so on, till it works out the correct answer, except for a big tree that could take potentially forever, and most of that calculation would make almost no difference to the final result. What you can do is place a terms limit. A terms limit doesn't limit the total number of added and subtracted terms. Instead, it limits the size of each batch. So let's say I set a terms limit of 10,000. Program would add every combination of every cut set probability together, subtract every combination of 2, and so on. It might get to, say, every combination of 7 minimal cut sets and find that there are more than 10,000. More than 10,000 combinations of 7 minimal cut sets. So that batch, that 7th order batch of terms has exceeded the terms limit. So the calculation will stop there, and the program will return the result after adding in every combination of 5 minimal cut sets. So add all the sets together, subtract combinations of 2, add combinations of 3, subtract combination of 4, add combinations of 5, the last positive set of terms that didn't exceed the terms limit, and it will stop. But why wouldn't it stop at the 6th order term? Why wouldn't it stop after subtracting every combination of 6 minimal cut sets? Well, that's because if you subtract every combination of 6 cut sets and stop there, the result of your calculation will actually be slightly below the correct answer, meaning that your fault tree is returning a result that is a little bit optimistic, which particularly for safety scenarios is a no-no. You don't want a result that's underselling the risk in your system. So it returns the last upper bound set of terms that met with the target, that met with the terms limit. So it's ensuring that your result is never going to fall below what is the correct answer, whatever that happens to be. So one of the other concerns, though, is, well, how do I know that that result is accurate? You know, the program might, I might click OK and run that analysis, and okay, fair enough, it's giving me this as the probability that my top event will occur. How do I know that's accurate? Have I got a high enough terms limit? Could I be missing terms that I need? Should I be doing more? How can I tell that that's the case? Well, there is an option in there where you can ask the program to do a lower bound calculation as well, where it will return the result after the last set of negative terms. So in my hypothetical example, that's the 6th order terms. If there's a big difference between the answer the program is giving and the lower bound result, then maybe you need more terms. If there's very little difference, maybe not. So I can have a look in my results. And there's the result of my fault tree. If I look at my lower bound result, you can see actually there is a small difference. It's a little bit lower. It's a little low level of precision, but maybe I could stand to ramp up the terms limit a little bit. So I'll do 1,000,000 terms and see what that gives us. I'm going to run that. You can see it's a little bit slower than it was before because there's more numbers to crunch. It's still not too slow because I've got a nice new laptop primarily. But yeah, we got to the answer. And if we have a look, my result has not changed at any level of precision that I can see. I can up the precision in my results if I want to, but I'll leave it as it is for the example. But if I look down at my lower bound value now, that's a bit closer. It's gone further along. So now the two numbers are closer together than they were before. So that lower bound calculation is a way of just double checking that the terms limit you're using is returning an accurate result. So that is the cross product. In principle, if you run the cross product right up to the end, it will give you the exact correct answer. But of course, if for very big trees with lots of sets, that may not be practical. So you have these options to help you get to an accurate result in a much more practical period of time. But what if you've got a tree that's so complex and so big that even a sort of truncated cross product isn't getting you close enough to the right answer or isn't getting you to the answer quickly enough? An alternative is to use the Esary-Proschan approximation. So this is based on the idea of working out what's the probability that no cut sets happen and subtract it from 1. That should be basically the same, shouldn't it? What's the probability that at least one cut set happens? Or what's the probability that no cut set happens but subtract it from 1? Should give you the same answer. Again, that would be an oversimplification. I'll explain why. There is a reason this is called the approximation and not the right answer. But the idea is that I can work out the air. So if I add this sort of box around my Venn diagram from earlier, inside the circles is the probability that at least one cut set happens. And then the gray part is where no cut sets happen. If I can work out this part, the gray area, and subtract it from 1, that should just leave me with what's in the circles. So the probability that a cut set doesn't happen is 1 minus the probability of that set happening. Then do that for all the sets, multiply them together, subtract from 1. This is a much simpler calculation than the cross product, because in a cross product we said we're adding and subtracting and so on, bigger and bigger sets of terms. Here, I'm just, for every cut set, I just add another multiplication, just a big string of multiplied terms, subtract from 1. Much simpler. It's simple and efficient, but like I mentioned before, there is a catch to that, which I'm not showing on the slide, but I'll explain a little bit in a moment. I'm going to jump out again, go back to the software, because while I can manually tell the program to use the Esary-Proschan approximation, I'm not going to do that. I'm going to illustrate how the optimum upper bound works by reducing the number of terms in my terms limit. Because what the program is going to do, it's going to try the cross product with a terms limit of 1,000, and it will also try the Esary-Proschan approximation. Whichever one of those two methods returns the lowest result, that's the result the program will show. The reason being that both of these methods are what we call upper bound methods. Both of them can only give you either the correct answer or something that's a little bit above the correct answer. They can never go below it, which means that whichever one is the lowest, that must be the most accurate. It must be the one that's closest to the correct answer. So I'm going to reduce my terms limit, which should make my cross product a bit less accurate, basically, because I'm doing fewer terms. So it's going to be higher above the actual result. So I'm going to do that. I'm going to run my model again. Anybody who's observant might notice that immediately that's actually a bit higher than it was before. It was 9344 earlier. Now it's 9348. I look at the results summary. I can see there's my result. If I scroll down, the program actually tells me it's now using the Esary-Proschan approximation. It's found that in this scenario with the lower terms limit, that's the method that's giving me the most accurate result. But why is it higher? So why is it higher than the cross product? Why is it giving a result that's not exactly correct? This all comes down to one of the fundamental principles of probability theory. Again, I'm going to sort of make you relive the trauma of school with some of the things that your teacher would have told you. Remember those coins that we were flipping earlier? In order to calculate the probability that at least one coin lands on a particular value, or that all of them give you the same outcome, you would use things like the addition law or the multiplication law. In order for those to work, the events involved must be independent of each other. Now, if I flip two coins, the outcome on coin 1 is independent of the outcome on coin 2. So I can use these probability ideas, these probability laws, to work out those probabilities. Are minimal cut sets independent of each other? The answer to that is that in most cases, in most fault trees, the answer to that is no, they're not. You get situations where minimal cut sets will have the same event in them. So these 3 minimal cut sets here all have this ECT1 event in them. Minimal cut sets are not always independent of one another. In fact, I'd say it will be rare to find a serious fault tree where all the minimal cut sets are independent. That is where the catch is with Esary-Proschan. It has only a limited capacity to deal with dependency between cut sets, which is why you usually get a slightly higher answer from Esary-Proschan. It's not dealing with that interdependency. And that doesn't mean it's not the end of the world necessarily. If a fault tree has very low probabilities, so if the events and the minimal cut sets have very low probability, as you might find, for example, in, say, an aerospace sort of safety fault tree, where the probabilities of failure tend to be quite low, then that impact of dependency between events and sets is largely mitigated. The lower the probabilities in the tree, the less the impact is of dependency between sets on the result of the Esary-Proschan approximation. So I've seen it over the years in big aerospace fault trees in particular. People use Esary-Proschan because it's fast, and because the probabilities are so low, it's accurate as well. So even though there are catches to these methods, it doesn't necessarily mean you can't use them, especially not if you're dealing with very low probabilities. Incidentally, cross product can deal with interdependency between cut sets. That's why that's the one that will give you the exact correct answer if you're able to solve the whole thing. Again, I'm not going to dig into the details of that. That was the oversimplification that I mentioned earlier, that I'm not considering the kind of dependency between sets. but the cross product will deal with that, whereas the Esary-Proschan approximation doesn't. But in this example, my terms limit is quite low, so the cross product result is coming in quite high. As it turns out, the Esary-Proschan is giving me a more accurate outcome. And the program has done that automatically. It's done both calculations, looked at the results and said, okay, here is the one that is giving you the most accurate outcome. And it's telling you, this is the method I've used. So if you're not happy with it, you can always go back, adjust your options, see if you can do any better in a practical analysis time. So back in we go again, and there's one more method that I haven't talked about, and that is the rare approximation. This, for want of a better term, and a term I'm less likely to regret using later, this is the one that will give you the sort of quick and dirty result. Here, the program will simply add together the probabilities of all the cut sets and just stop there. Think of it as kind of the first iteration of the cross product calculation, just adds all the sets together and stops. Now this naturally is very, very quick. You don't have to do all those different terms for that you get with the cross product. You don't even have to sort of reverse the probabilities as you do with the Esary-Proschan. Just a simple summation, and that's it. Naturally, that's going to be the least accurate of the three methods. But if a tree is very, very big and you have low dependency between sets, or the probabilities are very low, again, the result may still be pretty close to the correct answer. So in this instance, I'm kind of treating my areas as if they're independent of each other, almost as if there's no overlap between them, and just adding them all up instead. I'm going to hop back to the program one more time. I'm going to go into the project options, and I'm going to just manually select the rare approximation. And I'll run it. And naturally, that's done very quickly. You can see that result is noticeably higher than what we were getting earlier for both the cross product and for Esary-Proschan. So because of the dependency between sets and the fact that probabilities are relatively high, that's coming in not terribly accurate. But like I said, the lower the probability of the cut sets and the events in your fault tree, the more accurate that method will become. So those are the methods the program uses to get you to a result, an accurate result, as quickly and efficiently as possible. And I guess the main learning points there, the things I'd like you to take away, the cross product. This is the one which, if solved in its entirety, will give you the exact correct answer. It's just that for very large fault trees, solving the cross product in its entirety is perhaps not terribly practical. So you can set a terms limit that will stop the calculation once it reaches a certain number of terms in a batch, and return the last set, the result after the last set of positive terms. So it will be accurate, but it will never be below the true answer. It will always only be exactly the correct answer or a little bit above. The Esary-Proschan approximation, based on the idea that you can just work out the probability that no sets occur, subtract it from 1. Again, faster than the cross product, depending on how much dependency there is in your tree and the probability, how high the probability is for the different sets and events, may be more or less accurate. But for both of these methods, you have the lower bound method to test for accuracy. Finally, the rare approximation that just gets you to the answer the quickest way possible. Mostly that's useful for very large fault trees with a lot of cut sets, where the probabilities are quite low. So to finish off, talking about sort of what sets the fault tree analysis aside in FaultTree Plus from other tools, I'd like to talk about some of the additional analyses that take place or that can be done alongside the conventional fault tree calculation. Because we've chosen our options, run the analysis of the fault tree, and we've got back a result, and the program's telling us that the probability of the top gate, the top event occurring, is 9 point something 10 to the minus 4. But we might want to learn more from our fault tree than that. We might want to learn which of the events are causing the biggest problem, which of the events is our system most sensitive to. There are tools in the program that will help you identify where the weaknesses are in a system and also potentially the strengths. What parts of the system should you consider more redundancy? Which parts of the system could you actually kind of ignore because the system is not terribly sensitive to them? And that's where these methods come in. So one last time, I'm going to jump back to the analysis, and I will, for the purpose of this, just go back to what my settings were at the beginning. Optimum upper bound with 10,000 terms limit. That's going to give me the nice accurate cross product result. Run that. And I'll take a look in my results summary and take a look at the importance results. Two values in particular, the Fussell-Vaselli importance and the Birnbaum importance. Fussell-Vaselli indicates the contribution of each event to the overall probability of the top gate. So for example, I can see this event is contributing to about 48% of failures, this one to about 16%, and so on. These results are a function of how many cut sets each event appears in, what the probability is of that event. So essentially, it's the overall contribution. How likely is it that a minimal cut set will feature that event? How much is it contributing overall? The Birnbaum importance is a measure of how sensitive the top gate probability is to changes in a given event. So the higher the Birnbaum importance, the more the impact will be on the top gate if that event were to deteriorate. So higher sensitivity means that if you let that event get worse, the system will suffer more as a result. Now we might ask the question, if I know that a particular event is contributing a lot to my top gate, doesn't that just mean that my top gate is very sensitive to that event as well? Yeah, it's not unusual for an event that has a big contribution to have a high Birnbaum importance as well. But it is also possible for an event with a low contribution to have a high sensitivity. An event that doesn't contribute much now, but if you let it get worse, that will have a big impact on your system, because you can see these events here contribute more than this one, but their sensitivity is less. It's kind of alerting you to where potential, I guess, hidden dangers might exist in your system. Events which don't cause much of a problem now, but if you just decided, oh, that event doesn't matter, it's got low contribution, I'm going to ignore it, I won't do any maintenance, I won't do an inspection, you will start to see problems because your system is sensitive to that event. So Fussell-Vaselli and Birnbaum together can tell you quite a lot about your system architecture, about which events contribute a lot, but also about which events could contribute a lot if you didn't look after them. These two values are very useful, but in a way, a little bit abstract. Two numbers that we're supposed to look at and understand what they mean. What if we could see directly what impact we would get if we were to, say, change a particular event or event value? That's where we can use a tool in the program called special sensitivity analysis, another pretty unique point that the FaultTree Plus software has. Go into analysis and I can do a special sensitivity analysis. So let's say I want to do that for my top gate, and I just want to see what the impact would be if I were to play around with the failure rates of the events in my tree. So I can tell the program, I want to see the impact on the unavailability, the probability of the top event, if I were to change the failure rate. And I'll be able to see then, almost like I'd made the changes manually for real, what the impact would be on the top gate if I increased or decreased the failure rate of each event in my fault tree. So I'm going to say try 5 different multiplying factors. I can set these manually, but I'm just going to keep the defaults. So what if I reduced my failure rates to 1% of what they were before, or 10% of what they were before? Or what if I multiplied my failure rates by 10 or 100? What impact would that have? So I can run the analysis, go to the results, and I can then look at each individual event, and I can see how the top gate unavailability is expected to change as I modify the probability or the failure rate of that event. Some events, like this one, may not show much difference. Maybe the system is not very sensitive to that event. But others, like this one at the top here, you can see a much greater impact on the overall probability of the top gate if I were to increase the failure rate of that event. Those are just based on the importance analysis data that we saw earlier. Now, there was one last thing I wanted to talk to you about, but I do realize now there was one thing I said I would mention, which I haven't touched on, and it does actually relate to something I said right back at the beginning, which was to do with the modularization and why that makes the results more accurate. It all just ties back to the terms limit. If I try to solve the probability of my top gate based on 10,000 or 100,000 minimal cut sets for that gate, the cross product calculation would be huge, and I would very quickly hit the terms limit, and I'd start throwing away huge chunks of my calculation. However, if, wherever possible, I solve individual gates on their own, those calculations are much smaller and individually far less likely to hit the terms limit. So with modularization, I'm less likely to hit the terms limit because I'm generating far fewer product terms in my calculation. Therefore, I'm a lot less likely to throw away big chunks of my calculation. So the cross product with modularization is a kind of marriage made in heaven because it allows you to make the most of the cross product without the threat of running into the terms limit and losing accuracy. So yeah, in a moment we'll go to Q&A. There is just one final point I want to make, and that's to do with the Peak Avenue platform. So as many of you might know by now, we're moving towards the Peak Avenue platform, kind of browser-based platform for a variety of reliability and quality methodologies, which will include, of course, fault tree analysis. And a question might be, if we're moving to this browser-based environment, are we going to be watering down the fault tree in any way? Or are we going to be making compromises? And the answer to that really is no. The engine that drives reliability workbench FaultTree is being dropped into the Peak Avenue platform. So cut set analysis, probability analysis will work the same way. The same methods will be there. So you'll still be able to rely on that, so those same quick, accurate results, just with the grunt of those big cloud servers behind it. Yeah, that was the final point I wanted to make. And I think that leaves us with a little bit of time just for question and answers. And I appreciate we've touched on a lot of fairly advanced stuff there quite quickly. So I'm happy to take any questions you might have.